Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 26th video lecture, and today we want to pick up where we left off, which was talking about pointwise convergence for a sequence of functions. And we were talking about wondering if certain properties that the sequence of functions has would be inherited by the limit function, and this involved interchanging limit processes. And we're now going to look at some examples where certain properties aren't necessarily captured by the limit functions in general. And we're going to turn eventually, during this lecture, to something called uniform convergence for the sequence of functions that will ensure certain characteristics for the sequence of functions are inherited by the limit function. But anyway, we're going to start off with some examples of where interchanging limit processes matters, makes a difference. So we're going to start off with this. So as an example, we'll say for m equal to 1, 2, 3, and so forth, and n equaling 1, 2, 3, 4, and so forth, define a sequence S sub m comma n equal to m over m plus n. So this is a sequence of two variables. And so here's the thing to notice about this sequence. It says for any fixed m, note that the limit as n goes to infinity of m over m plus n, that will be equal to, so m are fixed, we're letting n get bigger and bigger and bigger. That'll go to 0. So if you take the limit as m goes to infinity, and then before that, take the limit as n goes to infinity of m over m plus n, you'll get the limit as m goes to infinity of 0, which equals to 0. But if we interchange the limit processes, we'll get a different result. Namely, for any fixed n, note that the limit as n goes to infinity, as m goes to infinity of m over m plus n, well here this will be infinity over infinity. You could use L'Hopital's rule here, take the derivative top and the derivative bottom with respect to m. And what you'll get is, it'll be 1 over 1, and that limit is 1. So, the limit as n goes to infinity of the limit as m goes to infinity of m over m plus n will be equal to the limit as n goes to infinity of 1, which equals to 1. Okay? So here, you can see that interchanging the order of taking the limits of this sequence of two variables results in two different answers. Okay? And let me write that down. So the limit as m goes to infinity, the limit as n goes to infinity of m over m plus n does not equal to the limit as n goes to infinity of the limit as m goes to infinity of m over m plus n. Okay, another example I'd like to look at is the following. we're going to let f sub n of x be defined on 0 to 1 and by f sub n of x is equal to x to the n. Okay? Now note, f sub n of x, which is equal to x to the n, it is continuous on, or for each, I'll say on 0 to 1, for every n element of the set of natural numbers, J. Now, for each fixed x element of 0 to 1, not including 1, okay, then f sub n of x as a sequence converges to 0. As the limit as n goes to infinity of f sub n of x would be equal to the limit as n goes to infinity of x to the n. And since this number is 0 or in between 0 and 1, then when you raise that to higher and higher powers, it's closer and closer to 0. Now, when x equals to 1, then it's pretty clear that f sub n of x, which is f sub n equals 1, okay? Well, that's 1 to the n, so that's just equal to the sequence that's always 1, and so that converges to 1. Right there, here. Converges to 1. So the sequence f sub n of x, which is defined to be x to the n, converges pointwise to this function, I'll call it f of x, which is equal to 0 if x is an element of 0 to 1, and converges to 1 if x equals to 1. And so what this is an example of where the f sub n's are all continuous on 0 to 1, but what it converges to, the limit function, f is not continuous on 0 to 1. For this is not continuous at 1. So I'll say this, so pointwise convergence does not preserve continuity. Let's look at another example. let's let f sub n of x be equal to x squared over 1 plus x squared raised to the n, where x is real and n is equal to, here we'll say 0, 1, 2, there. Okay. Consider f of x equal to the sum, as n runs from 0 to infinity, of f sub n of x, which equals to, of course, the sum, as n runs from 0 to infinity, of x squared over 1 plus x squared raised to the n. Now, the first thing we'll observe is that, note for x equals 0, f of 0 will be equal to 0, because this sum will always be 0. Okay? And as f sub n of 0 equals to 0 for all n. For x being different from 0, then the sum, as n runs from 0 to infinity, of x squared over 1 plus x squared raised to the n will be equal to, well, the x squared here is a constant with respect to the index n, so I can pull it out. Raised to the n. And you can think of all of this being raised to the n. So I'll say that's the same thing as x squared times the sum is n runs from 0 to infinity of 1 over 1 plus x squared, all that raised to the n. And notice that this quantity right here is positive, and no matter what x is, it's positive, and we're raising it to the nth power, but yet it's less than 1. So it converges by the geometric series. So that's equal to x squared. What does it converge to? Its first term, which is 1, over the ratio, which is 1 minus the ratio. So it's 1 minus 1 over 1 plus x squared. And so that's the same thing as x squared. If you do a little work here, that's times. The algebra work is 1 plus x squared, which will be in the bottom, and here it will be x squared in the bottom. And then that will cancel out, and you're just left with 1 plus x squared. So let me summarize this as the limit function, the sum function. So, the sum function is f of x equal to 0 if x equals to 0, and 1 plus x squared if x is different from 0. So, what this shows is a convergent series of continuous functions, for each f sub n was continuous. May have a discontinuous sum. That's what that's an example. Well, I'd like to look at a different example, one having to do with derivatives here. If we let f sub n of x be equal to sine of nx over the square root of n, and this is where x is an element of R, and n is equal to 1, 2, 3, forever. So if we look at that type of sequence of functions, then we note that the limit as n goes to infinity of L sub n of x will be equal to the limit as n goes to infinity of what this was, which was sine of n times x over the square root of n. This is as n goes to infinity. Now, what happens is that sine of n times x is going to bounce between -1 and 1. But then we're going to be dividing it by things that are going towards infinity. So this goes to 0. And that's true for each fixed n. Okay? Thus, L sub n of x, this particular sequence of functions, converges pointwise to f equal to 0. Okay. Now, note that if you take the derivative, f prime of x, you're going to get 0 because the derivative of 0 is 0. Okay. Now, let's look at the derivative of f sub n of x. Now remember, this is what f sub n of x is. So when I take its derivative with respect to x, here's what I'm going to get. I'm going to get cosine of, well, the n in the bottom, square root of n, is a constant. So I just write down 1 square root of n, which is the square root of n in the bottom. The derivative of sine is cosine of nx, but then we've got to take the derivative using the chain rule of nx, and so that's n, which of course equals to, if you want, so the f sub n's derivative is equal to the square root of n times cosine of nx. Now, we look at when x is equal to 0, then the limit as n goes to infinity of f prime of x, this one x is equal to 0, is equal to the limit as n goes to infinity of really the square root of n, which equals to infinity. Okay, so that does not exist as a real number. So we can make a conclusion based on what we've done for this example. Namely, we could say, so this is an example of a sequence of functions that are differentiable. And whose limit function is differentiable. But the limit as n goes, but the, I guess what I want to say is, but f sub n prime of x does not converge to f prime of x. Okay? Pointwise. So the limit function was f. All right. I'd like to look at another example. We're going to let f sub n of x be equal to n times x times 1 minus x squared raised to n. And we're going to let that be defined on e equal to 0 to 1. And we're going to consider n equal 1, 2, 3, forever. Okay, so let's talk about these sequence of functions. We notice that the limit as n goes to infinity of f sub n of x will be equal to the limit as n goes to infinity of n times x times 1 minus x squared raised to the n. Now, if x equals to 0, then this limit as n goes to infinity of f sub n of x, well, this will be 0, and so what you'll get is 0 every time. Now, if x is equal to 1, similarly, then the limit as n goes to infinity of f sub n of x will be equal to 0. Because when you take 1 in squares, you get 1, 1 minus 1 is 0, 0 to the nth power. That's going to be 0. And so we just get 0 here. But what happens for all the other x values in this domain of this function? If 0 is less than x is less than 1, then the limit as n goes to infinity of n times x times, I think it's 1 minus x squared raised to n, will be equal to, when you take out the x from the limit, the limit as n goes to infinity of n times 1 minus x squared raised to n. Now, here, this will be going towards infinity. Okay? This part right here will be a number in between 0 and 1. And when you raise it to higher and higher powers, that goes to 0. So that's an indeterminate limit form. And so what we'll do is we'll rewrite it as the limit, well, I'll say x times the limit as n goes to infinity. Well, the way I'll rewrite it is n over 1 minus x squared raised to the minus n. So you think of this as in the bottom as 1 over 1 minus x squared raised to n. And then n's going to infinity. So that part goes to infinity. And the bottom will end up going towards infinity as well. Okay? Okay, And so then we can use L'Hopital's rule. And taking the derivative of the top with respect to n is no problem. Taking the derivative of the bottom with respect to n, well, that involves something called logarithmic differentiation. So here we're going to have one. I'm not going to show logarithmic differentiation, but essentially you'd let y be equal to 1 minus x squared raised to the minus n, and then ln of y, so I'm not going to show it to you, is equal to ln of 1 minus x squared raised to the minus n. You bring down the minus n, then you differentiate both sides. So I'm not going to show it to you. So ln of y is equal to minus n times ln of 1 minus x squared, and then that says that 1 over y, and we're doing the chain rule here, the y prime is equal to, now I take the derivative of this is minus ln of 1 minus x squared, and then solve for y prime, I multiply both sides by y, so I got y, or minus y, times ln of 1 minus x squared, and then remember the y is this guy, so we get is equal to, so here's the derivative. Again, I'm not showing this to you. It's 1 minus x squared, I guess I am showing it to you, minus n ln of 1 minus x squared. And so that's what I'm going to write here. So it is 1 minus x squared to the minus n ln of 1 minus x squared, and then it's had a minus sign with it. I forgot this minus sign. So this minus sign here. Okay? That's what we have. Okay? And that's equal to x times the limit as n goes to infinity. This can be rewritten as minus, pull the minus to the top, we have 1 minus x squared to the n over ln of 1 minus x squared. Okay. Now this is just some number. As n goes to infinity, this is going to go to 0. So what that tells us is f sub n of x, which is equal to n times x times 1 minus x squared raised to the n, converges pointwise to 0. That's what it tells us. Now we look at the intervals. Now, the interval from 0 to 1 of f sub n x dx, that's going to be equal to the interval from 0 to 1 of n times x times 1 minus x squared raised to the n dx. Okay, the n can be pulled out. Here, you can integrate this by use substitution. Here you'd have something raised to a power. Here's almost the derivative of something. But to be the derivative of something, we need a minus 2. So I'm going to say, I pulled out the n, I'm going to have 1 minus x squared raised to the n times minus 2 x. So here's this x. I'm putting in a minus 2 dx. I'm putting in a minus 2, so I have to compensate by putting a minus 1 half out front so they combine and multiply 1. 0 to 1. Now I have something raised to a power derivative of the something. And the answer to that, in terms of integration, is, if you will, minus n over 2, well, that's outside. And here, this would be the something raised to one higher power all over that new higher power. And I have to evaluate that from 0 to 1. Okay, and then when you stick in 1, you're going to get 0. And when you stick in 0, you're going to get 1. So minus a minus n over 2 times 1 over n plus 1. So that ends up being n over 2 times the quantity n plus 1. That's what I get. Right. And so the limit as n goes to infinity of the integral from 0 to 1 of f sub n of x dx. That's going to be equal to, well, it's going to be the limit of this. Let me write that down. That's going to equal to the limit as n goes to infinity of n over 2n plus 2, which equals to 1/2. Use a little closer. Okay? But the limit as n goes to, I'm sorry, I should say the integral from 0 to 1 of the limit of f sub n dx is going to be equal to the integral from 0 to 1 of 0 dx. We talk about pointwise convergence, and that's just equal to 0. Okay. So this was an example of a sequence of functions f sub n that converge pointwise to f, but the sequence of intervals of f sub n, doesn't converge to f So in this last example, what we're saying is the limit of the integrals doesn't equal to the integral of the limit. Well, next we want to give a definition for a different type of convergence that really will maintain a lot of properties, not all properties that we're looking to maintain. And so the type of convergence we're going to be talking about is called uniform convergence. So here's its definition. It says we say that the sequence of functions f sub n as n runs from 1 to infinity converge uniformly on E to a function f if for every epsilon greater than 0, it's for each, I like for each better, there exists an integer big N, it's really an natural number, such that for all n greater than big N, f sub n of x minus f of x will be less than epsilon, and that's for all x element b. That's the definition. Before I move on, let me say, and I'll emphasize this with a picture in just a second. You know, the difference between pointwise convergence and uniform convergence is that, you know, we have these for each epsilon there exists this n. Well, for pointwise convergence, the n might depend on the x. You have to get a different n, maybe for different x's. But here for uniform convergence, one particular n, will work for that particular epsilon. And it doesn't depend, the n does not depend on x. So in essence, and I'll show this pictorially, basically you can get a band around F what we're saying is, if we have F, this is F, the limit function, then if you take some epsilon units about that, so you could have epsilon above and epsilon below, and eventually there's some spot in the sequence of functions f sub n, the left sub n, such that from that spot on, we'll call that spot the n, all the functions will be within this band. So f sub n plus 1, it might curve around, but it's in this band. F sub n sub 2 is in this band as well. All of them. And for every x, it'll be in this band. Okay. Well, let's do an example. Well, let's consider, first of all, let's start off with a previous example we talked about. Consider f sub n of x equals x to the n. And here, well, it's not exactly the same example. Here I'm going to look for x being an element of 0 to 1, where we don't include 1. Now, f sub n of x converges pointwise to 0 on that domain. Now let's look at it pictorially, and we'll see that it does not converge uniformly. So pictorially, here's what it looks like. You know, if this is 1, and this is 1. This is f sub 1. It's a straight line. It's x raised to the first power. Y equal to x. That's f sub 1. F sub 2 is x squared. It looks like this. Then we got, and I made that one too. Too much of a curve. Here's x raised to the third, f sub 3, f sub 4, down like this, and continue on like in that fashion. And so here, if I put a band around 0, you see that there isn't a particular spot in the sequence such that for all the x's in between 0 and 1, not including 1, including 0, that they will be in this band. Because no matter what no matter how far along we're going in the sequence, eventually, for x is really close to 1, we will have output values that are close to this 1. Okay? But point-wise, I can make them go towards 0. In particular, to show that it's not uniformly convergent on 0 to 1, not including 1, what I'll do is I'll produce an epsilon. I'll let epsilon be equal to 1/2. And then, if you note, if you take x equal to the n, I'm sorry, we let n be a natural number. then the n plus 1 root of 1/2 has the property that it's going to be less than 1 and yet bigger than 0. Okay? And so this is an x in that domain of these functions. Now, that particular x will show, those particular x's, you get big enough that this guy here, f sub n plus 1 acting on this guy, f sub n acting on this guy, okay, that will be equal to, so it will be 1/2 raised to the n, this is big N here, over n plus 1. And that is going to be greater than 1/2. And so, what we have is f sub n of x minus 0 is not, is going to be greater than 1/2. And that shows f sub n of x does converge uniformly to 0. How come? Because I can produce, okay? How come? Because I can produce an epsilon such that no matter what n you pick, no matter how far along you go in the system, there is an x in the domain such that that there is a f sub n of that x minus f sub 0 would not be within epsilon units of each other. The definition of uniform convergence is not holding. I can't remember what I've written for the definition of uniformly convergence in terms of that absolute values being less than epsilon, but a lot of times we'll say less than or equal to epsilon. So for uniform convergence, okay, you could have f sub n minus x at conclusion minus f of x is less than or equal to epsilon. I didn't say that. And that's for all x under b. And we say the less than or equal to for convenience in terms of proving things. Well, I'd like to look at one more example. I showed an example that was not uniformly convergent, but let's look at an example that is. Same type of example, we're just going to change the domain. So if I have f sub n of x equal to x sub n on, here I look at it from 0 to 1/2, closed interval, then here's what we know. X sub n is going to be less than or equal to 1/2 raised to the n for all x's element of 0 to 1/2. And so we can show from this, we will show f sub n's converge uniformly to f of x equal to 0 on 0 to 1/2. The way we'll do that is we let epsilon be greater than 0 be given. We need an n element of the natural numbers. such that for all n bigger than or equal to just big N, f sub n of x minus 0 will be less than or equal to epsilon, and that's for all x element of 0 to 1/2. Oops. And so we want absolute value of x sub n minus 0 to be less than or equal to epsilon. That is, we want x sub n to be less than or equal to epsilon. Okay? But here's what I want you to notice. Note, for all for all x element of 0 to 1/2, we know that x sub n, as I said, x sub n will be less than 1/2 to the n. So if we can show that 1/2 raised to the n is going to be less than epsilon, then we're good. So we'll note, or we want 1/2 raised to the n to be less than epsilon. To solve for n in the exponent position, we use logarithms, so we want ln of 1/2 raised to the n to be less than, it's supposed to be less than or equal to, epsilon, and then that means we want n times ln of 1/2 by the property of logarithm to be less than or equal to epsilon. Now, ln of 1/2 is going to be a negative number, so when I divide by it, we have to switch the direction of the inequality. So we want n to be greater than or equal to epsilon over ln of 1/2. And I made a mistake. I forgot to take ln of epsilon. Gosh. So I should have taken ln of epsilon here. Take ln of epsilon here. So we want ln of epsilon divided by ln of 1/2. And we can do this at Archimedes property. We know that the set of natural numbers are not bounded above. So by the Archimedes property, there exists a big N element of the natural numbers such that big N will be greater than or equal to ln of epsilon over ln of 1/2. So for all n bigger than or equal to this big N, then it follows that the absolute value of x sub n minus 0 will be less than or equal to epsilon, and that's true for all x element between 0 and 1/2. Okay, I know we're running a little short on time, but I'm going to extend this to at least get one theorem down that's kind of a familiar type theorem and about uniform convergence. So here's the theorem. It's called the Cauchy criterion for uniform convergence. Here's what it says. It says the sequence f sub n, the sequence of functions, f sub n defined on E converge uniformly on E. It's an if and only state, if and only if statement. converge uniformly on E. If and only if, for each epsilon greater than 0, there exists an integer n such that for all m and n greater than or equal to this big N, f sub n of x minus f sub m of x will be less than epsilon, and that's for all x element of E. Let's do the proof. If and only if statement, let's start this direction. We're going to suppose f sub n converge uniformly to this direction isn't so bad. On E to F, okay. We let epsilon be greater than 0 be given. Okay, and then we're looking for this integer, right? But then there exists an n element of J such that, because of uniform convergence, such that f sub n minus f sub n of x minus f of x will be less than epsilon over 2 for all x, for all n greater than or equal to big N and x element of E. And so, thus, for all n and m greater than or equal to big N, what we have is that the absolute value of f sub n of x minus f sub m, and this is for all x element of E. That quantity is going to be equal to f sub n of x minus f of x plus f of x minus f sub m of x, which is going to be less than, by the triangle equality, f sub n of x minus f of x plus f of x minus f sub m of x, which is going to be less than, and here I guess, I should have said less than or equal to before. So less than or equal to epsilon over 2 plus epsilon of 2, you can say less than, which equals to epsilon. Okay? And that proves this part. Now to go backwards, here we're going to suppose that for any epsilon greater than 0, there is an integer n such that for all n and m bigger than or equal to n, and f sub n of x minus f sub m of x, okay, will be less than or equal to epsilon or less than epsilon, we'll say less than or equal to. And that's for all x element of E. Then, what we'll say is for each x element of E, f sub n of x forms a Cauchy sequence. Okay? Which converges in R. I'll say which converges. That's in R, it's in C. Okay. Thus, for each x in E defined, f of x is equal to the limit as n goes to infinity of f sub n of x. So this gives us a prospect for the limit function for the uniform convergence. Okay. Okay. Now we want to show that this sequence converges uniformly. I'll write right here. To f of x So how do we do this? We're going to use the definition. We let epsilon be greater than 0 be given. Okay. We need a natural number. Big N such that for all n bigger than or equal to this big N, that's the value of f sub n of x minus f of x will be less than or equal to epsilon, and that's true for every x element of E. Okay. Well, by assumption, in this direction, by assumption, we know there exists an n element of J such that for all n m bigger than or equal to this big N, f sub n of x minus f sub m of x will going to be less than or equal to epsilon for all x element of E. Okay. Now what we're going to do is we're going to fix n element of J. Fix n that's bigger than this big N. Okay, so fix it. And then we're going to let the limit as m goes to infinity for this quantity. And the claim is that the limit as m goes to infinity of the absolute value of f sub n of x minus f sub m of x is the same thing, so I'll write right here, equals the absolute value of f sub n of x minus f of x. And that's for all x element of E. For each X element. So we're going to prove this claim. So here we're working on the proof of claim. So here's what we got. We're going to let delta be greater than 0 be given. We need a natural number, designated as K. K such that for all m bigger than or equal to K, we're talking about a limit here. That is that the absolute value of f, the absolute value of f sub n of x, minus f sub m of x, minus the absolute value of f sub n of x, minus f of x will be, inside f would be less than epsilon. Okay? Okay. And that's true for all x element of E, for each one of them. Okay? Now, here, I'll say it this way. This is true for each x element of E. Now, what I want to tell you is that you'll notice that this quantity, the absolute value of f sub n of x, minus f sub m of x, minus this absolute value of f sub n of x, minus f of x, that can be shown to be less than or equal to, I'll write it right here. It's the f sub n of x minus f sub m of x minus f sub n of x minus f of x inside absolute values. That's what can be shown here. Less than. And so I should have put this in parentheses. This guy minus this guy without absolute values. And that's just equal to the absolute value of f, so I'll write it this way, f sub m of x minus f of x. It's really minus this quantity, but the absolute value of that is still this. Now, since f sub m of x converges to f of x for each x in this point line, okay, then, no, we don't have any more, so it's pointwise. Then there exists a case of x that's an element of the set of natural numbers such that for all m bigger than or equal to this case of x, the absolute value of f sub m of x minus f of x will be less than delta. And so that ends the proof. And that ends the proof of claim. Okay. So now getting back to the main theorem, including its proof. Since f sub n of x minus f sub m of x is less than or equal to epsilon for all n, m greater than or equal to n, and for all x element of E, okay, then the limit as n goes to, as m, I should say, goes to infinity of f sub n of x minus f sub m of x inside absolute values will be less than or equal to epsilon but we know for each x that absolute value is the same thing, that limit is the same thing. That implies. We're almost done. That implies I'll just say thus f sub n of x minus f of x is going to be less than or equal to epsilon for all n greater than or equal to big N, and for all x element B. That shows f sub n of x convergence uniformly to F on E. That is the proof. Long proof, long lecture. Thank you very much for your time and patience.